In the previous class, we have seen what is Hamming window and what is Hanning window. Okay, so two different windows we have seen. So basically, here we are seeing the window technique for designing the FIR filters. So in that window techniques, first of all, we have seen a rectangular window, then Hamming and Hanning window, and now today we will see Blackman and Bartlett window. So there are different windows. So these windows main motive is to design a filter that is having minimum transition width, okay, or it should be having minimum error. Whatever pass band approximation errors are there, that should be minimum. Our main motive is to use that only. So after going through different window functions, if a given specification is there for a particular window, particular low pass filter, so if we are going to design the same low pass filter by using different window functions, we will be getting different values of n and different values of the magnitude, you can say that pass band attenuation and stop band attenuations. So that will be deciding like what is the uh, uh, you can say error with respect to the ideal low pass filter. So from there we can compare the different design methods, like which one is closely relating to our given specifications. So before that, uh, as we have gone through the Hamming and Hanning windows, we will see some questions based on the Hamming and Hanning window, and then we will be proceeding to Blackman and Bartlett window. Okay. So here a question is given. You need to design a high pass filter. Okay, so you need to design a high pass filter using Hamming window, and here the cutoff frequency is given to be 1.2 radian. Okay, so here omega c is given 1.2 radian, and m value, that is order of the filter, is given to be 9. This is order of the filter. Okay. So once the cutoff frequency is given and order of the filter is given, what we can do is, so before starting filter designing, we should be having the frequency response of that filter. Okay. Frequency response in terms of h e to the power j omega, it should be given. If it is given, we can proceed to find out the hd of n, and then we will be multiplying this hd of n by using a window function that is given into the question, and that will be giving you out the impulse response of our desired filter. This is impulse response of desired filter. Okay, so our main motive is to find out this. Once we have found out this, we can proceed further to find out h of z. Okay, this is the transfer function in terms of digital filter, FIR filter. Okay, so here in the question, cutoff frequency is given and m value is given, that is order of filter. So with respect to that, we will be finding out the uh, frequency response. Okay, so frequency response is given like h of e to the power j omega. Okay, so that will be some value when, so first of all, there is high pass filter. So we will see what is the high pass filter. So if high pass filter is there, so with respect to frequency, whatever its magnitude response will be there, magnitude response, it will be like, it is high pass filter meant initially it will be 0. Okay, initially it will be 0. So at this cutoff frequency, it will be passing the signal, otherwise it will be 0. So it will be if this is in the positive direction, then similarly it will be in the negative direction too. Okay, So we will design it into the negative direction. So if we are plotting this in negative frequency direction, so it will be 0 up to a frequency that is minus omega c, and after that it will be having a magnitude. Okay, so this magnitude is generally considered to be 1, okay, unity, that is magnitude, and here it will be minus pi. So whatever frequency response will be there, that will be periodic in nature, so it will be having a period ranging from 0 to pi into the positive frequency direction, and 0 to minus pi in terms of negative frequency. So overall it will be having a period of 2 pi. So whatever frequency response is there, that will be periodic with respect to 2 pi period. Okay, so this is a basic high pass filter magnitude response. Okay, so from there omega c value is given. Okay, omega c is given, so whatever we will be having a magnitude, so this magnitude is defined by e to the power minus j, because it is linear phase, so it will be minus j omega, that is frequency, into, that is called m minus 1 divided by 2. This is the generalized form of uh, filter that is having a high pass filter or low pass filter. Its magnitude to be 1, so this is defined by this, and this is defined when the frequency, your frequency is ranging between, you see, sorry, ranging between omega c to pi. If this is the frequency range, then this will be the magnitude. Similarly, if the frequency in the negative side, it is ranging between uh, minus omega c to minus pi. If this is the frequency range, this will be the case. Otherwise, it will be 0. Okay, so we can call, or otherwise it will be 0. Okay, so this is the generalized high pass filter uh, frequency response. So here generally m minus 1 by 2 is considered to be alpha. We will be writing alpha for m minus 1 divided by 2. Okay, so with respect to that, we will see its frequency response first. So if omega c is given and m is given, with respect to that, the generalized frequency response will be like hd e to the power j omega will be e to the power j omega alpha. Okay, so here alpha is m minus 1 divided by 2. Okay, so generally what we do, m, we make it as odd. We always try to make m should be odd. Okay, then only m minus 1 divided by 2 will be a uh, you can say a complete integer. Okay, so our main motive is m should be odd always, so whenever you see m is considered to be odd only. Okay, so and this time this will be the frequency range. Okay, so this is the frequency range in which a particular magnitude will be there, otherwise it will be a 0. Okay, so this is how the frequency response we will be uh, plotting, or you can say frequency response we should be deriving in once the specification cutoff frequency is given into the question, and also m value is given. So either we can put directly the alpha value, or this is the generalized. Okay, this is the generalized frequency response. Okay, so once we know the frequency response, we will be finding out the inverse Fourier transform. Okay, by using inverse Fourier transform, we will be finding out the hd of n. So hd of n will be given by 1 by 2 pi integration, that is ranging from minus pi to pi hd e to the power j omega e into whatever hd is there, okay, into e to the power j omega n into d omega. So this will be the formula we will be always using to find out the hd of n. And after putting these values, okay, and with respect to the value, hd of n is defined only in this frequency range, so we will be breaking it into minus pi to omega minus omega c. This will be the given, otherwise it will be 0, and again it will be having a magnitude of e to the power j omega alpha when it is ranging the frequency omega c to pi. So after solving this, we will be getting, after solving and simplifying these terms, we will be getting in this term. Okay, so here we can see if in the below term it is n minus alpha. Okay, so when n is equals to alpha, then below term will be 0 and above term will also be a 0 value. Okay, so we will be avoiding this. So we have to find out n equals to alpha. For n equals to alpha, we have to find out the hd of n separately. Okay, so that will be finding out by taking the limit into this same expression, and from there we will be getting this as the value. So for n is equals to alpha, this will be the value, otherwise this will be the generalized value expression for hd of n. So once we have found out the hd of n, okay, we have to find out h of n, that is the desired impulse response of our given filter specification. Okay, with respect to that, it will be whatever hd of n we have got into the window function multiplied. So window function will be multiplied by hd of n, we will be getting the h of n. So here in the question it is given like we have to use Hamming window. So the expression for Hamming window is, we have already seen. So this is the expression for Hamming window. Okay, so this Hamming window will be multiplied by hd of n that we have obtained. Okay, so after multiplication we have to finally find out the h of n. Okay, either we can find the expression, or so expression will be this value for n not equals to 4. After multiplying these two, that will be the value. If n is equals to 4, whatever Hamming window function is there, that will be multiplied by 1 minus omega c by pi. Okay, that will be our h of n. But finally we have to find out the coefficient of this impulse response. So these are the coefficients. Okay, coefficients of h of n, that is whatever our desired impulse response is there, we have to find out the coefficients. So by putting the different n values, we will be finding out the coefficients. Okay, so after finding out the coefficients, it can be seen like the coefficients that we have found are symmetrical along the n equals to 4. So it is symmetrical along the n equals to 4, that we can see. So once we have find out it is symmetrical along the n equals to 4, if we need to find out the magnitude response, okay, so the formula for magnitude response is, we will be finding out the magnitude response in terms of omega. So generally it is given like whatever n value is there, okay, from 0 to uh, whatever m minus 1 divided by 2 is there, it will be whatever h of n is there into cos omega n. Okay, so generally we do like this. This will be the magnitude response general, but here it is symmetrical along the n equals to 4. So once we will be putting, so that symmetrical values are combined together, so 2 times it will be whatever h of n its value is there, that will be 2 times. So after combining, this will be the multiplication by cos omega n, and this is when h of 4 will be there. Okay, so h of 4, it is having a separate value. So this will be the expression to find out the magnitude response. So after putting this, we will get this as the expression. Okay, so here magnitude response is once we are changing the frequency. So magnitude response will be plotted with respect to the frequency. So this magnitude response will be plotted with respect to frequency. So once frequency is 0, what will be the magnitude? We will be seeing. So suppose for frequency is equal to 0, magnitude is this one. Okay, for frequency is 0. Similarly, for frequency is equals to 1, what will be the magnitude? Suppose this is the magnitude. Okay, so for 2, this one is there. So from this is for an example. Okay, so in this expression, by putting the different value of omega, we can find out the magnitude response. Okay, so this is how the magnitude response is to be formed. Similarly, we need to find out the transfer function. So to find out the transfer function, this is the jet transfer formula is there. So whatever h of n we have find out, we will be expanding it into multiplying z to the power minus n for n ranging from 0 to m minus 1. So this is how the expression will be. So after arranging, we can get the transfer function as uh, h of z. Okay, so in that h of z, we can write in terms of y of z and x of z. So h of z is given by y of z into divided by x of z. So after expanding, we will get uh, multiplication. This will be the term. So either we are writing in terms of y of z and x of z, or even we can write it in terms of h of z only also. Okay, so both are correct, whatever form we are going to write. Okay, so that was the question. In the second question, suppose we have another question. Here we need to design a band pass filter. Okay, to pass the frequency in the range 1 to 2 radian. Okay, using Hanning window. We need to use Hanning window for m equals to 5. So here we need to find out the band pass filter. So if a band pass filter is there, then its specification will be like this is omega and this is the magnitude response. Okay. So if it is band pass means a particular band of frequency will be passing. Okay. Otherwise it will be 0. Okay. So suppose this is omega c1 cutoff frequency 1, this is omega c2. So for omega c1 and omega c2 it will be passing the signal, that means it will be having a magnitude of 1, otherwise it will be 0, and this will be your pi. Similarly in the negative direction it will be this. Okay, so this will be minus omega c1 minus omega c2, and this will be minus pi, because it should be a periodic in having a period of 2 pi, so it is considered to be 0 to pi positive direction and 0 to minus pi in the negative direction. So this will be the generalized magnitude response of a band pass filter. So here the pass band frequencies are given to be 1 and 2. That means omega c1 will be 1 radian and this will be 2 radian. Okay, so this will be 1 and 2 and this will be pi. So this is how we should be depicting the given expression. So finally we can see how the frequency response. So first of all we will be finding out the frequency response. So that frequency response will be, it will be having a magnitude of e to the power j omega alpha. Okay, this is the generalized one that we have seen in the previous question, and that will be magnitude only when the frequency is ranging between omega. Okay, so there will be like the frequency is ranging between omega c1 and omega c2, and this will be minus. Okay, so it will be between minus omega c1 to minus omega c2. Okay, otherwise it will be 0. Okay, this is how the magnitude response should be given. So once we have the magnitude response, sorry, the frequency response, we will be finding out the hd of n, that is impulse response, or the this will be like impulse response, we call it hd of n, that will be impulse response, or we call it the coefficients. It will give you the coefficients of your hd of e to the power j omega whatever given. Okay, so this hd of n we will be finding by using the Fourier transform method. Okay, this is, sorry, so this is the inverse Fourier transform. We are considering the inverse Fourier transform, that will be giving you the hd of n. So 1 by 2 pi, okay, minus pi to pi, this will be the expression. So by putting different frequency ranges ranging from minus pi to pi with respect to the given condition, we will be expanding it and solving the same by taking the integration. Okay, so again into the below side we can see it is n minus alpha term is given. So same we have to find out for n equals to alpha separately. So here alpha value will be m minus 1 by 2. So m here is 5, so 5 minus 1 by 2, so that is 2, 4, 4 by 2 is equals to 2. So for n equals to 2, we will be finding out the hd of n separately, and for other terms, it will be given by this value. Okay, so once we know the hd of n, again we will be multiplying it with respect to the Hanning window expression. So for Hanning window, the expression is this one. Okay, this is the expression for Hanning window. For n equals to ranging from 0 to m minus 1, and we will be multiplying these two. After multiplication, we will be putting the n value for different n value, n equals to 0, this will be the expression. Okay, it will be coming out to be 0. So for n equals to 2, 1 and 2 3 4. Okay, so this is how we will be finding, and we can see here is uh, for n equals to 4 it is this. So n equals to 4 and 0, 1 and 2, these are the impulse response that are symmetric with having a center frequency of n equals to 2. Okay, so these are symmetric along the two n equals to 2. So with respect to that, we will be plotting the magnitude response. So that will be again a bit symmetrical. Along with that, we will be making it to 2 into 2 times we will be making, and cos omega n will be there, and n should be ranging from 0 to m minus 1 by 2, and this will be for h of 2 value. So h of 2 will be taking out separately, because this h of h of n, that is h of m minus 1 by 2, or we call it here, it will be the n value seems to be equals to 0. Okay, so this will be giving you out the 0 value, otherwise that will be positive or negative. So this is combining n equals to 1 to this value, and this will be coming out to be for n equals to 0 type. Okay, and for all other values it will be here. So after putting this, we can get the expression. So after putting the expression, this is coming out in terms of omega. So again we have to plot the same magnitude. Okay, so this magnitude will be with respect to the omega. So for omega equals to 0, we will be putting 0 into this, and whatever coming out to be, that will be the value similarly. Okay, so this is how the magnitude plot is there, and similarly we will be considering the transfer function by using the jet transform. Okay, and we will be separating it out and finding out the jet transform. So this is how the basic calculation should be going through for calculating or finding out the FIR filter transfer function or FIR filter impulse response. Okay. So up to here we have seen the examples of Hamming and Hanning window. Now we will see what is Blackman window. Okay, so in Blackman window, similar to other windows, it will be having a fixed mathematical formula. Okay, so window function are having a fixed mathematical formula. So here in that fixed mathematical formula, so one thing, this filter designing is basically an approximate method. So this filter designing is not an exact filter designing. Whatever exact specification is there, we cannot design the exact specification practically. Okay, so suppose we have to uh, get a value that is like its coefficient is like 0.5. Okay, if it is 0.5, so once we are going to implement it practically on the hardware. Okay, if we are going to implement this 0.5 by using a hardware in digital system. Okay, once we are going to use digital system, in that if we are going to implement it, it might be like we should, instead of 0.5, we will be getting 0.4999, similar to this. We would not be getting the exact value. Okay, so this is like, this filter designing is an approximate analysis or approximate design. Okay, so that's why there are different window functions. All the window functions are having some different properties, like in terms of transition width, or we can say in terms of main lobe width and side lobe height. So with respect to different main lobe width and side lobe height, different windows are defined. So with whatever specifications is given into our question, with respect to the specification of filter designing, we will be proceeding. We will be checking whether which window function is going to be having the minimum number of errors. Okay, and that can be utilized effectively to design a particular specification. So we will be seeing that. So that's why we are going through different type of filter designing techniques. Okay, so in that, in the Blackman window, what we are going to do is we are having the same function. Okay, so whatever function is there, we have to, our main motive is to same design a rectangular window, whatever approximation is there. So or we can say like the whatever uh, window function we are going to design, our main motive is to restrict the number of samples available into the impulse response of our desired impulse d of n. So in hd of n, whatever, it is having infinite number of samples. So our main motive is to reduce it by using a rectangular window to a finite number. So instead of rectangular window, we will be using different type of windows, and it is having different advantages and disadvantages. So in this case, like suppose this is the expression of Blackman window. Okay, so in that, this is for case of causal window. If it is a non-causal, the same, the range of n should be ranging between uh, minus m minus 1 to minus m minus 1 by 2 to m minus 1 by 2. Otherwise we will be making it to be n equals to 0 to m minus 1. So if it is n equals to 0 to m minus 1, it will be a causal form. Okay, so we will basically focusing on the causal form only. Okay, so suppose here we are considering n equals to 0. if we are making this n equals to 0, then for n equals to 0, the w of n value will be, okay, so w of n, whatever window function is there, that's its value will be 0. Okay, so this will be this one plus this one into this one. So the window function that will be started with is, okay, similar to this. This will be the window function in case of Blackman window. But in the previous cases, we can see uh, in the Hamming and Henning, we can see like it was having uh, one is having 0.5 in both the cases. So if it is 0.5 in both the cases, it will be again having, yes, it will be having again the 0. But in case of this term, this one is an extra term, okay, into the Blackman window. It was like this one was in the Hamming and Henning window. So in that, if we are putting n equals to 0, there was a magnitude. It was not going to be 0. Okay, so in that case, if this is the value of 0.08, okay, so in that window, type of window, uh, Hamming window, that magnitude, whatever response, if we are going to plot into the window function, it will be starting with this, okay, and going up to the this. So it was having an offset value, like, okay, so to reduce this offset value, initially we should be requiring some extra hardware to implement this 0.08 magnitude. Okay, so to reduce this, Blackman window is proposed, and that added this term, and this will be making sure like when n equals to 0, your window function value is 0. Okay, so it will be starting with a 0 value. So this is how different window functions have been derived to depict like what are the advantages and disadvantages. So in that case of um, window function, the main lobe width is given out to be 12 pi by m, and the peak of the side lobe is given out to be minus 58 dB. So after combining all the window functions, suppose we are going to find out, from there we can consider which one is good in terms of main lobe width and which one is good in terms of side lobe height. Okay, so another window is the Bartlett window. So into the Bartlett window, it is the window function. Suppose in case of non-causal case, if we are considering separately, it will be coming out to be 1 plus n and 1 minus n. So n 1 plus n is there when n is ranging from minus m minus 1 by 2 to 1. If n is ranging between 1 to m minus 1 by 2, then it will be 1 minus n. So this is how the different window functions are defined. So if we combine all the window functions, okay, so in that after combining, we can see there are different window functions. In that, we will be finding what is the approximate transition width of the main lobe is there. So what is the advantage? Like the advantage is, if we are having this is the frequency response in that. Okay, so this is your main lobe width, and this is your, this height is side lobe height. So if this main lobe width is less, that means that window will be better. Okay, and also in terms of this, if this side lobe height, or you can say the peak of the side lobe is less, then it will be better. Okay, so in terms of that, we can see if a rectangular window or Bartlett window are there, its main lobe width is given out to be, in the rectangular window it is 4 pi by m. M is the order of filter. Okay, so here m is the order of filter. Okay, and the minimum stop band attenuation. So in the stop band, the minimum attenuation will be this value. So this will be the attenuation up to this we can achieve. Okay, and this is the peak of the first side lobe. Okay, so whatever side lobe are there, this is having the minimum side lobe height. Okay, so this is like, from there we can compare different type of window functions, Okay, so that as we are proceeding further, in case of Bartlett window, it is 8 pi by m. Okay, and this is having the stop band attenuation that is coming out to be minus 25. Okay, and in terms of peaks, side lobe height. Okay, so this width. Okay, so this width is minimum here in case of 4n is there. This is 8n. This is 8n, and Blackman window is having the maximum width. Okay, the side lobe width is having maximum one, and similarly, the attenuation that we are getting is the maximum attenuation is achieved in terms of Blackman window, and along with that, we are having the side lobe height that is minus 58. Okay, so that is highest in case of Blackman window. So we are considering, like we can see here, the main lobe width should be minimum. Okay, but the attenuation should be maximum. But here we can see, like if the main lobe width is maximum, okay, because this is should be minimum to have a better approximation to an ideal filter, but it is having higher main lobe width, but at the same time it is having the minimum, you can say, height, side lobe height. So there is an we have to compare these different characteristics of different window functions, and we have to find like which window function is going to satisfy our specification. So in the specification, suppose it is given like the maximum, you can say the main lobe width. Suppose a question is given like we have to find, design a filter that is having a main lobe width that is less than uh, 8 pi by m. Okay, suppose this is the uh, given specification into the question. Suppose we need to have a filter that is having a less than main lobe width having less than or equals to 8 pi by n. So this is satisfied by the filter, I would say the method that is window function 1, this rectangular, Bartlett, and Henning and Henning. So these are the different window function that is satisfying this condition. But also in that question, it is given like the maximum peak that we can get age should be uh, greater than, suppose, 35. In terms of negative, suppose we are requiring greater peak side lobe height is there, or we can say peak of the side lobe, if we that is having a higher side lobe peak. Okay, so if this is the case, then we have to satisfy these two conditions. Either it is equal to or less than 8 pi by m. So these are the four contenders. Out of that, we will be satisfying the second condition, like we should be requiring a peak that is greater than minus 35. So a peak that is greater than minus 35 is your these two, but out of that, this is having a higher width, so that is not satisfying our question given specification. So only this is going to satisfy our specification. So we will be using Hamming window to design this specification into the question. Whatever question is given, whatever specification of the filter design is given, so this is the specification, and this specification is satisfied by the Hamming window. So we will be using Hamming window for designing the filter. Okay, so this is how we should be deciding if the in the question it is not given like which window function we should be requiring to design a particular filter. Okay, so and based on that we will see some questions. Suppose it is given an FIR linear phase filter. So whatever filters are given to be designed, or we are going to design, that will be basically the linear phase system. So linear phase means it will be having a magnitude that is will be of the form e to the power j omega alpha. Okay, so this is the phase, this is the phase, and this in this whatever e to the power j theta, it will be behaving like a j theta. Okay, e to the power minus j theta. So this theta will be your omega alpha, this will be your phase. Okay, so this phase is directly proportional to omega, so it will be a linear phase system. So it is saying like an FIR linear phase filter has the following impulse response. So this is the following impulse response, and it is saying like it is having a linear phase system. So we need to find out the filter. So here use Bartlett's window and compute the impulse response of the filter. So we need to find out the impulse response, means we need to find out h of n. Okay, and find its magnitude and phase response as a function of frequency. So along with the h of n, we need to find out the magnitude plot also and phase plot also. Okay, so for the magnitude plot, we have to find out h of omega mod. Okay, so whatever this is there for different omega value, so it will be having different omega value. We will be finding this magnitude response, and phase will be h of omega the same. It will be like phase, and for different it will be also for different omega value. We have to find out. Okay, so we will proceed. So hd of n is already given. Okay, so if hd of n is already given, we can find out the same your that case here the magnitude response that we are going to find out is in terms of uh, 1 plus cos omega mod. So once we are going to find out, we have to find out first the h of n. So this h of n, we will be getting like h of n will be hd of n multiplied by the Bartlett window that we have studied into the previous slide. Okay, so from there, for different n values, we will be getting a different Bartlett function. Okay, so this is having like n is ranging from 0 to 4. Okay, so n is positive. So by using this, okay, so for n equals to 0 to 4, okay, in terms of here, so this is m minus 1 by 2 is 4. So m minus 1 by 2 is 4. So m will be here given out to be, if we are getting the m value, it is given out to be the 7. Sorry, this is 9. Okay, so m is 9 here, we can say. So n is to be ranging from 1 to 4. Okay, so once we are putting n equals to 0, sorry, 1, 2, 3 and 4, we can get this as the expression. Okay, so from there we can get the Bartlett window function, and once we know the Bartlett window function, we will be multiplying it with respect to 1, and that will be your h of n. Okay, so once we know the h of n, we can find out the magnitude. Okay, so from there, once we find out the magnitude, it will be given out to be 1 plus cos omega. Okay, so your h of omega magnitude will be given out to be 1 plus cos omega. So from there, that will be the magnitude. So for different omega value, so we will be putting omega value equals to 0, pi by 6, pi by 4 and up to pi. So we are considering only the positive frequencies. Okay, so we are considering only positive frequencies because your hd of n is also given only in the positive direction only. Okay, so we will be considering only the positive frequencies. So for different omega value, we will be putting, and we can get the magnitude response. Okay, so this is how the magnitude response is calculated, and we can plot this magnitude response in terms of omega. Okay, so this is how we should be plotting different omega for different magnitude. Okay, so this table value can be plotted with respect to different frequency, and similarly we will be finding out the phase. Okay, so to similarly to find out the phase, we can get like, so here, this is here. Okay, so once we know the h of uh, n, we can get the magnitude response, or we can get h of omega. So this h of omega, whatever real part is there, okay, and imaginary part are there, we will be separating. Okay, so this phase of h of omega will be given by your whatever imaginary parts are there, and what is the real part we can get from there, and it will be coming out to be minus 2 omega. Okay, so once we know the minus 2 omega, here the complete phase is given to be from pi to minus pi. Okay, so here negative and both positive frequencies are considered. So in that case also, if we are going to consider the negative frequencies, it will be the same one. okay, coming out to be in the negative direction. So by putting a different frequency value, we can get the different phase value, and we can plot its phase by combining all the points, and it will be given to be the phase response of that filter. Okay. This is the question, the same one. It is being solved. So here, h of n is so this is how the Bartlett window for n equals to this is given. So this one is like so the first step will be our h of n finding. So for that we will get okay. So one thing is this is the form of a causal form. So in the previous slide we can see here this is the form of non-causal Bartlett window is there. So in case of causal window, Bartlett window, this will be the expression. We can note it down. So this is your causal Bartlett window. Okay. So this is causal form. So here we can, because it is defined in the positive frequency range, we can basically we have to use all the time the causal only. So from there, once we are defining the causal, it will be coming out to be this function. So in that, we have to find out m minus 1. Okay. So m minus 1 will be equals to 4. So from there, m is coming out to be 5. So if we are using the non-causal, okay, if we are going to use the non-causal, then the m value will be a different one. That will be in terms of the complete range. Okay. So it is coming out to be a 9 in that case. Okay. So if we are using the causal window function, basically all the time we should be using the causal only one. Okay. So once we are using causal window functions, this m is coming out to be 4, and this will be the expression for the causal window of a Bartlett window. And once we know the Bartlett window, we will be putting n equals to 0, 1, 2, 3, and 4. Up to 4, we will be putting, and finally we will be combining hd of n into the Bartlett window function, and after multiplication, we will be getting h of n. So with respect to that, h of 0, h of 1, h of 2, h of 3, and h of 4 we will be finding out. Okay. So once we have find out the coefficients, these are called the coefficients. Okay. So once we have find out the coefficients in terms of phase and magnitude, this is the generalized frequency response. Okay. So this is the generalized frequency response in terms of the coefficients. If coefficients are given, we will be coming out to be this. Okay. So in that case, in the magnitude response, we were only considering this. So this is the magnitude, and as it is given to be, it is a linear phase system. Okay. If it is linear phase system, means it will be given by e to the power minus j omega into alpha. Okay. So this alpha will be m minus 1 by 2. This will be giving out to be your phase. Okay. So from there, once we will be putting m equals to